Hello everyone, my name is Partho Das, Assistant Professor, Electrical Engineering Department, JS College of Engineering, West Bengal, India. So in today's class, we are going to do the problems on Thevenin's theorem and maximum power transfer theorem. So in the previous classes, we have separately done what is Thevenin's theorem, what is the steps to follow to solve the Thevenin's theorem, then how we can solve, what is the procedure, then those things we have done. And after that we have done in the another class, we have done the what is maximum power transfer theorem, what is the proof for maximum condition of maximum power transfer theorem. So those things we have done. So in today's class, actually it is a practice session where we are going to solve, and we were going to see how we can solve Thevenin's theorem and maximum power transfer theorem. So now one question may appear to you that why when we have done the concept of Thevenin's and maximum power transfer theorem, that time we have done both things separately, but when we are doing problems on Thevenin's and maximum power transfer theorem, so at that time we are going to solve both theorems together, because the reason is that the basic funda of that maximum power transfer theorem is that Thevenin's theorem. So the procedure to solve any maximum power transfer theorem is basically the Thevenin's theorem. So if we do together this Thevenin's theorem and maximum power transfer theorem, so then I think it is very easy to understand about the concept, and very easy to remember. So how to solve the Thevenin's theorem and maximum transfer theorem. So let us start today's class how to solve Thevenin's theorem. So to do that, first we will going to see what is the statement. That thing already we have seen, but for now we are just take 1 to 2 minutes to recap all the concepts that we have in Thevenin's theorem, and that we are going to use for the solve of Thevenin's theorem as well as the maximum power transfer theorem. So let us start. Yes, this is the definition of Thevenin's theorem. So what is told that, so basically thing is that in Thevenin's theorem, so any complicated circuit which have, whereas we have different series parallel combinations resistor are there, we are basically in this particular class we are basically dealing with the circuit which has only DC source. So if we have only DC source, that means we have in the circuit we have only resistors. So here in this particular class, we are going to deal with the DC source, maybe voltage, maybe current, and with that we are going to deal with the only the resistor. So any complex circuit can be reduced to a simple series circuit which may contain equivalent voltage source, equivalent resistance, and load resistance. So in Thevenin's theorem, we have already seen that a complicated circuit is reduced to a simple series circuit which contains a VTH, RTH, and RS, all are connected in series, and then we find out whatever we want to find out: load voltage, load current, uh, load power, and at a different load condition, what is the load current, load voltage, those things we can find out. Those are the advantages of Thevenin's theorem. So let us see how we can what is the procedure we have to solve any Thevenin's theorem. So let us start. Yes, procedure to for solving this Thevenin's theorem. So as you can see in the diagram, to find the load, so as you can see in the diagram, what you can see, follow my pointer. So it is written that this is a complicated linear DC circuit, correct, denoted by a dotted box, that is a black box it is told, and with that complex circuit we have, there is a connection of a load resistance, that is this Rn, correct. So now our aim is to find out what is the current flowing through this Rn and what is the voltage across this Rn. So if it is our aim, then what we have to do, what is the procedure to solve this Thevenin's theorem. So already we have discussed. So initially we have to disconnect the load resistance through which we have to find out the current or voltage. So first initially disconnect that, they made that terminal open, and find out at that open terminal what is the voltage value. So that voltage is known as the VTH, already we have done. So see, follow my pointer. Again, this is a complicated DC circuit. Yes, I have told we are going to deal with only DC source, so that means the circuit will be DC circuit. the terminal is open, so there is a voltage that is known as the VTH, Thevenin's voltage. Okay, so now we have to find out what is the voltage across over here. Now this is case for the first step. Now in the step 2, what we have to do in the step 2, see this, yes, this one. In the step 2, we have to view from the terminal from where we have disconnected the load resistance, and from there you just find out, what is the equivalent resistance of the circuit, provided that you have to remove all kind of sources from the circuit. All kind of sources means whatever voltage source or DC source, voltage or current source we have in the circuit, that we have to disconnect to find out the what is the equivalent resistance of the circuit viewing from the open terminal. Okay, so this is the step 2. And at the end, so after viewing this circuit from this open terminal, we will get a equivalent resistance. So in the first step, what we have got a VTH, that is the equivalent voltage. In the second step, we have got equivalent resistance, and at the end, after that, see, yes, so now our equivalent circuit is like this. We have reduced the whole circuit like this way. There is a VTH, there is RTH, and there is a terminal AB from where we have disconnected the load resistance. So now this, if we connect at terminal AB a load resistance, so then we can say that this is a simple series circuit. So now in the simple series circuit, if we want to find out the current, it is a very easier one. So just apply the Ohm's law, V is equal to IR, so I is equal to V by R. So just applying that thing, we can find out the uh, equivalent the load current through the load resistance. So as you can see, so any complex circuit is reduced to a simple series circuit. So that is the main concept. Already we have done this one. So now we have to do that. Yes, this is a diagram. So here you can see that there is a VTH, there is RTH, and there is RL. All are connected in series, and very simple. Say follow my pointer. There is IL, that is by Ohm's law we are applying over. IL is equal to VTH by RTH plus RL. So this is the, again, okay. So load voltage, if we want to find out, so load current into load resistance, IL into RL. So again IL value is this one, VTH by RTH plus RL. That thing we can put, and power absorbed is I square, IL square into RL. So those things we can do. Now this we have recapped how to solve Thevenin's theorem, because we need both things for maximum power transfer theorem. At the same time, we need this for the Thevenin's theorem. So now we are going to solve Thevenin's problem, so that we can better understand how to solve a Thevenin's theorem. So for that, we have considered a circuit like this. So here as we can see that there are two sources. So one is, there is a voltage source, there is a current source, and four resistors are there, R1, R2, R3, and R4, as you can see in the diagram. So here R2 is showing us the RL. That means through that particular R2 or RL, we have to find out the current. So as per the rule we will go. So what is the rule? So the rule is that we, through which we have to find out the load current. So that resistor from the circuit, initially we have to disconnect and find out at that open terminal what is the voltage value. So that will be our VTH. So that is our aim for the first step. So let us see what they have done. Just check, just follow my pointer. So see, so there is a resistor R2 that we have disconnected and made that terminal open. So there is a terminal AB, and now we have to find out what is the voltage across this point. This is the VTH. Now see the voltage at AB node, AB terminal. Can we say that that is actually the voltage difference between A node and B node? At A node we have some voltage, at B node we have some voltage. So and the difference between these two voltage will give us the voltage difference, and that is the terminal voltage. Actually we do that, this is the potential difference. So our aim is to that, If a circuit is like present like this, then we have to, what we have to do, we have to find out what is the potential at node A and what is the potential at node B, and the difference between these two will give us the whole potential at that terminal, correct? So that thing we have to find out. So here, so node B means this one. So first of all, we have to find out what is the voltage across this C, because whatever is the voltage across C, that voltage is appearing over here, because see, this terminal is open over here, so whatever potential is C at node C, that is actually at B. So here, to find out the potential of B, we have to find out the potential of C, and this see, this A terminal is directly connected to a voltage source. So at node A, we have a voltage of 3 volt. So whatever voltage source is directly connected to this node, so that voltage is appearing over here. So we can simply apply over here a KCL. Okay, so see, so applying any method we can find out. So at node C, so at node C, so see, just see, at node C, what are the voltage coming? So this voltage is coming, this voltage is coming, this voltage is coming, correct? These two are coming, and this is coming. So we know that at any node, total summation of incoming and outgoing current is 0. So I1 is the incoming current, I2 is incoming current, and there is a 2 ampere current. So all are incoming to the node. So we can say that 2 plus I1 plus I2, that is equal to 0. Now we doesn't know the value of I1 and I2, so we can convert that to a voltage quantity. So what is I1? That's I1, this is I1, see, this is the I1. I1 is equal to 3 minus Vc by 3. So what is the 3 minus Vc by 3? See, can we say that? So that I1 is equal to, this current is equal to the potential difference between the resistor connected, the resistor is connected between A and C terminal. Just follow my pointer, it will be very easier to understand. So this R1 resistor is connected between A and C pointer. So we can say that, so whatever is the voltage of A at node A, the voltage is this 3 volt. At node C, as we have a current source, so we cannot say that what is the voltage. So we can assume that there is a Vc voltage, correct? So we can say that the current passing through this R1 resistor is equal to the potential difference between 2 by the resistance value. So what is the potential difference? There is a 3 volt, and here we have assumed that at node C we have assumed that is a Vc. So between A and C node, the voltage difference is, see, this 3 minus Vc by 3. 3 is the resistance value. So as we can see over here. Now like this way we can uh, consider the I2 also, that is also 0 minus Vc by 6, correct? So from here we have calculated this 4 plus 2, that is a 6. So from there if we calculate, so the only one variable is there and all are unknown is there and all are known, so we can find out Vc. So now if we put if we know Vc, then we can find out I1 and I2 value, because only Vc is, we have to put the value of Vc into that equation. So like that way we can find out the I1 and I2 value, correct? So this is like this way we can find out. Yes, yes, yes. So after finding out the currents, that means we have, now we know, see, one thing we have to point out over here, see, I1 is minus 1 ampere and I2 is minus 1 ampere. See, in the previous diagram, the direction of I1 is from A to C, and from the direction of I2 is B to C. And after calculation, this is our assumption direction, and after calculation we have seen that the values are in negative. So what does that negative signify? That negative signifies the direction of the current. So whatever direction we have assumed, that is originally opposite. So that's why in the next picture what we have done, so we have changed the direction there. See, here is I1, here is I2, all directions are changed, reversed. Okay, And now we have to find out this VTH over here. VTH means this voltage and appearing this voltage over here, this voltage minus this voltage, whatever is the voltage over here at node B, it is actually the voltage at the wave point C. Okay, so if we do that, then it is coming that VTH is a VAG minus VBG. So VAG and VBG, correct? So what is the current value is coming? 1 ampere. What is the resistance value? Is 2. So 2 into 1 is 2 volt, and here we have the 3 volt. So 3 minus 2 will give us a 1 volt. So this is the result. So VT is a 1 volt over here. Correct? Clear my point? So like this way we can find out the VTH over here. Now coming to the find out the step, next step, where we are going to find out the equivalent resistance or the Thevenin's resistance at each of the circuit. So for doing that, first thing what we have to do, we have to make the circuit independent of any kind of source. So to make independent any kind of source, what we have to do, if we have a voltage source in the circuit, so remove that, leave it internal resistance in the circuit, and if it doesn't has any internal resistance with that, then what we have to do, we have to make the terminal short. And in case of ideal current source, if we want to remove that current source, make that terminal open, because and current source has its infinite amount of internal resistance in case of ideal current source. So when, as per rule, when a source is removed from the circuit, so it should leave its internal resistance over here. In case of ideal voltage source, internal resistance is 0. So when we are removing voltage source, we have to make the terminal short. And in case of ideal current source, we have uh, infinite resistance. So when we remove current source, we have to make the terminal open. So and now find out what is the equivalent resistance of the circuit. That is actually will give us the RTH of the circuit. That is the equivalent resistance of the circuit. Now let us see. See, this is three resistance we can see over here. So if we view from this node, then we can say that, so if we view, then we can say, so these two are in parallel with that, actually yes, these two are in parallel again with this R3, this R1 in series. So initially what we can say that R1 and R3 in series, and this whole combination is parallel with this R4. See, this is the RTH, R1 and R3 is in series, and with that this R4 in parallel. Now you can ask me how we have I have calculated, I have think about this in previous classes when we have done Thevenin's, or we have done the maximum power transfer theorem. So there we have discussed that how we can think. So viewing a terminal means, if we just, this is imagination thing, if we can think about that, uh, if a source is connected over there, how then, how a current can flow through that, through the circuit. So if we think there is a source connected between, follow my pointer, between node node this AB, so the current will come like this, it will divide. So this, the current passing through this R3 will come over this node. In this side, this is open terminal, so it cannot go. So like this way, it will flow through R1 and it will pass to this the terminal. So what we can say, this R1 and R3, same current is flowing through this R3 and R1. So as we know that if same current is passing through between two or more than two resistors, so they are in series. So that's why R1 and R3 are in series. And with that, this R4, as the current is dividing in between R3 and R4, so obviously this will be in parallel. So this is the case. So now we know this is VTH, we know RTH, we know. So we have to now sum up. So connecting this this VTH value of VTH, the voltage value, will act as equivalent voltage source. The value of this RTH will act as equivalent resistance, and we have to connect that load resistance that initially we have disconnected from the circuit. All three components should be connected in series, and simply we can find out the load current. Yes, so this is, you can see the circuit. There is a VTH, there is a RTH, and there is a RL. So now very simple way we can find out the ILC, the VTH, RTH plus RL. So now these values are given. 1.555 plus 1, that is 1 by 1, 2.55, that is 0.39, that is 39. Yes, this is the solution for the first problem. Now we are considering the yes, now we can find out the different things over there. See, so we can find out what is the current passing through. So now we know the load current, so what is the current passing through from there. So 0.39 ampere, so that we know. If we know the load current, we can find out the load voltage. Yes, this current in that resistance, and if we know that, we can find out the power also. So like this way we can find out everything. So if we know the VTH and RTH. Okay, so now this is the second problem. So I think you have understood many things regarding this, how to solve a Thevenin's theorem actually. So here I have considered a three source circuit to solve this Thevenin's theorem. So this theorem, again I am telling this theorem how to solve, but in a very little bit fast than the faster one, because already I have discussed with you everything. So just for better understanding, I am going to tell you that how this Thevenin's or maximum power transfer theorem can be solved. Yes, so this is the circuit and there is the RL. Follow my pointer, this is the RL. So from this RL we have to find out the uh, load current. So initially we have to disconnect this one and we have to find out this VTH over here. So see, this is the case. So here this is the open terminal. Now we have to find out what is the voltage is actually appearing at node A and at node B, and after that the difference between this node A and node B will give us the VTH of that circuit. And after that, when we are going to calculate the RT, that time we have to remove all the sources from the circuit and we have to view from that open terminal. See, now we are just going to see how they have solved. Okay, they have solved, they have applied the KBL. If after applying KBL, VBG, BG, so this is a, so we have to find out VAG and VBG, and the difference between VAG and VBG will give us the Thevenin's voltage. So first initially they have find it out AG. So AG is the 34 volt and BG is the 6 volt. So what is the VTH? AG minus BG. So difference between the two will give us that voltage. So AG minus BG will give a 28 volt. Correct. Now step 2. In step 2 what we can do? See, very interesting thing. So when we have to find out this RTH for a particular circuit, so what we have to do, we have to remove voltage source and we have to remove its internal resistance. Basically here we are dealing with the ideal voltage source and ideal current source. So that means after removing voltage source we have to make the terminal short, and after removing the current source we have to make the terminal open. Now see, in this particular diagram, if we remove the current source, so then we have to make the terminal open. So there is no utility of this branch. Correct. So the circuit will be reduced like this. Correct. Now if we view this circuit from this open terminal, so now you tell me, you just think what should be the equivalent resistance of this circuit. So if we think that there is a source is connected at over there at node AB, so how the current will flow, just think. So see, if we connect a source over here, just follow my pointer, it will waited to understand. So for, there is a source, so the current will flow like this. First it will flow passing through 2. At this node it will find out 2 to go, so it will divide. So we can say that 8 and 4 are in parallel, with that this 2 in series. See, this 8 and 4 in parallel, with that 2 in series. So now we know the equivalent resistance or the RTH of the circuit. Yes, now see, this is a very simple. Same way, this VTH, this RTH and RL, all we have connected in series, and we have find it out the IL. So like this way in each and every problem. So that means points to remember to how to solve this Thevenin's theorem and maximum power transfer theorem is that whatever is our circuit, so we will follow the rules of Thevenin's theorem. So what is the rules? Remove RL, make the terminal open, find out what is the open terminal voltage, that will be your VTH. In step 2, remove all the sources, make the circuit of independent of any kind of source, and view from the open terminal to find out what is the voltage value over there. And in the end, we have to connect this VTH, RTH and RL all connected in series and find out what is the load current. So like if we follow these 3 steps, these things, so it will be very easy to solve any kind of Thevenin's or maximum power transfer theorem. Now we are coming to, so this is all about the Thevenin's theorem. Again, yes, already discussed, yes. Now coming to the maximum power transfer theorem. So already we have discussed that how we can solve the Thevenin's theorem in details. Now maximum power transfer theorem, the concept of maximum power transfer theorem depends on this application of this Thevenin's theorem. It is an application of Thevenin's theorem, this maximum power transfer theorem. So we have, when we have just done the theory and proof of this maximum transfer theorem, there we have seen that when this internal resistance or the RTH is equal to the RL, so at that time we know that maximum power transfer can be delivered through the load resistance, correct? So that thing we have, that consideration we have, that formula we have derived, that derivation we have derived. So considering that concept, now today in the today's class we are going to see how we can solve this maximum power transfer theorem. So like this way, same circuit, DC resistive network is there and it is connected to some sort of load. Here it is shown that there is a variable load. So with the change of this load, when the maximum power, maximum current will flow through this load resistance, so that we can find out. And at that time, what is the voltage, what is the power across the load, that we can find out. So this is the circuit, simple circuit, where they have shown that VTH, RTH and RL all should be connected, and that is the derivation already we have discussed, so not going for that details. Okay, so coming to a particular problem directly. Yes, this is a circuit. This is actually, you can see that this is a complex one circuit. So as we can see, there is a 20-volt source and there is a 2 ohm uh, um, two voltage source and one current source is there. So two voltage source is 20 volt and 10 volt, one current source is there 2 ampere, and different resistance are there, 1 2 3 4 5 6 resistance. Within that 5 are internal resistance and there is a load resistance RL. So it is told that, so okay, for that particular circuit, find the value of RL that absorbs the maximum power from the circuit and the corresponding power under this condition. So we have to find out the maximum power. That means to find out that, we have to find out the maximum current, because the power formula is PL is equal to IL square into RL. So if we know the IL, then we can find out the PL. That is a load through power. Load power we can calculate. So what we will do, so if we want to find out IL through RL, so what we have to do, we have to follow the same steps as we have mentioned in the Thevenin. So what we have mentioned 2-3 minutes before, I have already told the same thing we are going to apply. So what we have done, they're just trying to remember. Yes, see that, so there is a RTH between RL, sorry, there is RL in between A and B terminal, so we have removed that one, we have made that terminal open, and now find out the VTH over there. So we will apply the Thevenin's rules to find out that. So we can apply KVL, we can apply KCL, we can apply, at the same time we can apply the concept of superposition theorem. So if we apply the concept of superposition theorem, then here we can considering a single source, we can find out VTH, and at the end we can connect all the VTH, but that is a lengthy process actually. So we are not going to for that details. Now here we are going to apply the KVL or KCL, so that very easily we can find out the equivalent the VTH of this particular circuit. Yes, so we can find out this, we are not going to for that details. Now see, it is applying the superposition concept. See, considering only one source, they have considered only 20 volt, they have removed the current source. Again at the they have removed the 10 volt source from this, from here, and they have find it out like this way. Only we can consider the current source, only we can consider the 10 volt, and like this we can find out the VTH over here. Yes, see, just see. So here it is 20 volt only considered, here only 10 volt is considered, and here only 2 ampere is considered, and in three case we have find it out three different terminal voltage, and by adding that three terminal voltage we will get the VTAC. This is, there is a minus 10 volt plus 5 plus 10, that will give us the total VTH of the circuit, that is 5 volt. So like this way, so there are different methods. So now you can ask me a question that how we can, how we can say that which formula should be used where. So that actually depends on you. So that actually comes to you when you are practicing and practicing, then you only able to understand where, how, and which formula can be used, so that the calculation will be easier and shorter. So that actually depends upon, it is up to you, but all are applicable, and if we use all applications, and that will give us the same result. So now, so after that we have to find out the RTH. So when we have to find out the RTH, that means we have to remove the 2 voltage source. With this 5 ohm we have a 20 volt, that we have removed. With this 10 ohm we have a 10 volt source, that we have removed. There is a 2 ampere current source, that we have removed, and after removed we have made the terminal open, and now view from this open terminal. So if you view from this open terminal, then we can say that, so this 10 and 10 parallel 10 combination, just follow my pointer, very important to understand over here. So if we think there is a source and it is, and you from that, so current is flowing, so at this node it will divide. So these two are in parallel, that current will flow through here coming to C, through this again it is coming to C. So these two are in parallel, adding over here, again it is dividing between this and between this. So some current is coming over here, and some current is flowing through this two, adding over here, and then it returning like this. So what is the serial parallel combination? So there is a current division, so these two are in parallel. Again there is a current division, so these two are in parallel. Now one thing we should say, the same current is flowing through these two. So initially, before these two are in parallel, these two are in series. So 5 plus 5 in series with this 10, correct? See, this is 5 and 5 in series, that is 10 with this parallel with this 10, and this whole combination in series with the parallel combination of this two 10. Okay, so this is the equivalent resistance over here. So like this way, this is VT, this is RTH, and this is RL, all you have connected in series, and we can find out the IL. Now after finding out the IL, we can find out the PL, that is the P max. So what is the formula? That is VTH square by 4 RTH. So now we know the RTH, we have calculated VTH, that we have calculated in the step 1. So like this way, so my point, as I have shown in the starting of this class, that maximum power transfer theorem calculation is depends on the Thevenin's theorem totally. So if we understand very easily and very perfectly how to solve the Thevenin's theorem, then there will be no problem with this um, maximum power transfer theorem. So I think everything is told to you, and it is very clear how to solve the Thevenin's theorem and maximum transfer theorem. So this is all for today. Thank you.